Sorry, Dylan, you can go in front of me. Okay, one thing that we haven't done the last 2 days that I probably should have done is talk about end behavior in a really formal way. We've talked about it every single day. We just haven't done it formally. And I think it's going to make a whole lot of sense to you guys now, because we've talked about it kind of really casually, and now the formal stuff, so you're going to go, oh, that's really easy. So let me sorry. Okay, so let's talk about the end behavior for this first graph. Well, we know, just looking at this graph, it's cubic. We know it's finishing pointing up, and it started pointing down. So in a formal way, we could say that as x approaches infinity, as x is getting really big, what's happening to the graph? It's going really big. It's going to positive infinity. Right? What's happening as x approaches negative infinity? As x gets really small, our graph started at negative infinity. Right? Isn't that exactly what we've been saying when we start our graphs every single time? And it's interesting, this is a cubic function. We know that any function with an odd exponent, they're going to start and end at different directions. So it's really easy to see here that these are opposites. Okay? Let's look at this one. As x gets really big, our graph's pointing down. It's approaching negative infinity. As x gets really small, our graph is also approaching negative infinity. This is a quartic function, degree 4. And what do we know about even degree functions? Same direction, whether positive or negative. In this case, they're both going negative, and we can see that with our end behavior. So they could either both be negative here or both be positive, depending on what the function looks like. Okay? Pretty cool. So I'd like you guys to try it, but I'm not going to give you the graph. If I give you some functions, some equations, you should be able to picture how they're going to start and end. It doesn't really matter what's going on in the middle for end behavior. So this first one, what degree is that? It's a 4th degree one. So I think as a table group, you guys should be able to come up with the end behavior. And then I gave you a challenging one, x to the 11th power. But it's odd, so you should be able to figure it out. Okay, so grab an expo marker, talk with your table for about a minute, see if you can do each of these. Let's look. So if we look at this 4th degree function, we first want to notice that it's positive. And if it's an even degree, we know that they're going to start and finish in the same direction. Because it's positive, that direction's up. Right? Doesn't really matter what's going on in the middle. But we do know it's 4th degree, so it's going to look, I have one too many in there. It's going to look like the letter M. Or W. Okay, there we go, W. So as x is getting really big, what's happening? It's pointing to positive infinity. Negative infinity for the x, it's pointing up. They're both pointing to positive infinity. That's what we're saying here. The other ones don't really matter to us right now. Yeah. So we really don't care about this stuff. The -7 does help us with our Y-intercept. It does do a lot to the graph, but for our purposes right now, this is all we care about. Okay. Let's look at the -x to the 11th. Has anyone tried to draw it? It's a fun one to draw. 11 is an odd number. It's negative. It's going to start, or finish down. Yep. Start up. And that means we're going to have 11 zeros. Okay. 1, 2, 3, 4, 5, 6, 7. There we go. So something like that. Okay? You didn't have to draw it. All we really care about where it starts, where it ends. As x gets really big over here, it's finishing down. As x went really small this way, it was starting in the positive infinity direction. Okay? Yeah. Okay, so let me say this one more time. f of x is just talking about the graph. What's the graph doing? So we have to look at this beginning part. This is saying when x gets really big, so that's saying this is the end of the graph. So it's saying what's happening at the end, it's going to negative infinity. This is saying when x is at negative infinity, that's this side. So that's the start. So at the end, it's going down. At the start, it's going up. That's the same thing here. I could have written these in reverse. I could have put negative infinity here and positive infinity there. It doesn't matter. Okay? More questions on that? Okay. I should have put this in your notes yesterday. I didn't. These are the only notes we're going to write. You guys take out your notebooks and just add that to yesterday's. Okay, you have 10 seconds to get your notes out. 10, 9, 8, 7, 6, 5, 4, 3. Quiet down, I'm going to be on the phone. Hello, Allison Wiz. Hi, good, thank you. So, today's objective is going to be to multiply polynomials. And the reason why we might ever want to do this is because we may want to put something in what's called standard form. So right now, we've been using what you might call intercept or factored form. That's when it looks like this. Right? I could square that, something like that. We might want to FOIL all that out so that we can get it into some kind of form. Like that. Okay? And typically in an Algebra 2 class, we'd actually start here and then go the other way. But with Common Core this year, we've tried going this way, and I like how it's been going so far, and I think you guys have been successful, so I think it's good. All right. When you've multiplied in the past, you've probably only used one method, and it probably depends on what your teacher preferred. I'm going to show you all three. You get to pick which one you want to use today. Okay? I'm going to use whichever one you guys tell me to use. So, all right. X plus 10 times x plus 5. That's an Algebra 1 problem, right? I bet a lot of you have used the box. That's an area model. We could do x plus 10 times x plus 5. Multiply, you get x squared, 5x, 10x, and 50. Combining your like terms, you would get x squared plus 15x plus 50, right? Look familiar? Okay. The next most familiar one's probably horizontal. That's FOILing, right? First terms, x times x. Outer terms, 5 and x. Inner terms, 10 and 5. 10 and x. Last terms, 10 and 5. When you multiply them, you get x squared, 5x, 10x, and 50. Those are exactly the 4 that are in the box, right? The box just organizes FOILing. That's all it is. Combining your like terms, you get the exact same answer. Okay? This middle one you maybe have never seen before. I don't know. It's kind of cool. I think you guys are going to think it's neat. If I was going to multiply, like way back in 3rd grade, 12 times 5. You guys remember how you did that in 3rd grade? 5 times 2 is 10. Carry the 1. 5 plus 1, you get 60. That's familiar? Okay, we can do that with algebra. So here's what we would do. Oops. We would stack your binomial. Okay? We would multiply the 5 times the 10 and the 5 times the x. So that's 50 and 5x. Then you would take the x and multiply it to the 10 and to the x. X squared and 10x. Why did I leave a hole here? I wanted to line up the like terms, And back to third grade, what do they usually tell you to put in the space? A 0. Did you guys ever understand why you put a 0? It's a placeholder, but going back to this problem, guys. Oh, I didn't do it very well. Let's make that 15. Okay, when I go to multiply this 1 times this 2, when I go to multiply this 1 times this 2, it's not really 2. It's not really a 1 here. This 1 is really a 10. That's why we put a placeholder, so that we really see it's 20. It's not 2. So there's a placeholder there because it's lining up our like terms. 5 and 2 here are like terms because they're both actually 50 and 20. So, okay. So then when we add together our like terms, which these are the same 4 terms that were in the box, we end up with this thing up there. Okay? I'd like to take a little vote and see which method you like best. So, hold on. We're going to raise our hands. Who likes the box method? Not that many. How many people like FOIL? No? How many people like vertical? Okay.
Does the vertical get hard though when you have more?
It doesn't really get any harder. It just gets longer, but not any harder. Okay. We're going to move on to this first problem. So, we have a cubic function. Does it have any double roots? Remember, double root skims the graph, -2. So we have the function f of x equals, we have 2 roots at -2. So I'm going to write x plus 2 twice. And then we have a root at 3. It's a single root, x minus 3. Okay? The problem is asking you to multiply it out into standard form. Okay? So I'm going to do this multiplication first of these 2. We'll multiply, and then we'll multiply by the third binomial. Okay? So if we do these 2 first, you guys like the stacking method. So we'll do x plus 2 times x plus 2. 4 and 2x. And then we're going to do this x times this 2. This x times that. So we get x squared plus 4x plus 4. I'm going to bring this term down that I haven't dealt with yet. Okay. All right, so now to finish the problem, we're going to multiply this trinomial by this binomial that we haven't used yet. So I'm going to stack it because that's the method that this class preferred. So we'll do it this way. I like to put the longer polynomial on top. Just makes it easier. So, yeah, -3 times 4, -12. -3 times 4x, -12x. -3 times x squared, -3x squared. Okay. Moving on to this x. This x times the 4 is 4x. So be smart about where we put it. We'll line it up with its like term. X times 4x. 4x squared, x times x squared, x cubed. Add together our like terms. So we have x cubed, 4 take away 3 is 1x squared, -12 positive 4 minus 8x. I had to think about it for a second. Minus f of x equals that. So what we're saying is this is exactly the same as when we had written our factored form. These 2 expressions are equivalent, exactly the same. Okay? You could type both of them in Desmos and they'd give you the same graph. All right, last step, what's our y-intercept? This form makes it really easy to find the y-intercept. Substitute in 0 wherever you see an x. So we're going to put 0 there, 0 here, 0 here, 0 here. We're left with -12. 0, -12 is our y-intercept. Let's look at our graph. Does it make sense? Ooh, no, it does not. What did we do wrong? Uh-oh. That does not look like negative 12 to me.
No.
I know what we did wrong. I just realized. This is a cubic function. It's finishing going down, right? It's negative. I should have put a negative right here at the very beginning. So what we can do, let's go all the way down to our answer. We just have to put a negative in front of our answer. We can do it like that. We can distribute the negative to everything too. Negative, negative, positive, positive. There we go. So our y-intercept is at positive 12. That fixes it. Okay. You could do the negative all the way at the end if you want. Yep. Not so bad. Okay, let's try one more. How about this one? We'll start this one, and then I'll hand out the worksheet because this is on your worksheet too. N plus 3 quantity squared. What does that mean? Okay, I'm going to take this. I'm going to put it on a different side just for 1 second. N plus 3 quantity squared. I'm curious if this is the same thing as n squared plus 9. What do you guys think? Okay, here's how you could check. We have a variable n. Can't n stand for anything? Okay. What's your favorite number? What do you want to pick n to be? Let's make it an easy number.
5 is easy.
Yeah, okay. I'm going to do 2 because it's easy. Okay. What if n was 2? Are these equivalent? 2 plus 3 is 5. 5 squared, 25. Is 2 squared, that's 4 plus 9. Those aren't the same. So what I'm trying to get you to see is that this is not true. That's not how this multiplies. Does it n plus 3 times n plus 3 mean this? So couldn't we stack them and multiply? If we multiply it out, we can get n squared plus 6n plus 9. So if we plugged in 2 here, we should get 25. 2 squared is 4. If I plugged in 2, we'd get 4 plus 12 plus 9, which is 25. Okay, so let's go back to our problem. Y equals, we just saw that this is the same thing as n squared plus 6n plus 9. So I'd like you guys to finish this problem. On your desk with your marker, multiply those. See what you get. All right, going over this problem, I'm going to go ahead and stack. Actually, you know what? On this one, I'm going to use the box. Just for the sake of using the box. All right, 2n minus 3 times n squared, 6n, and 9. The nice thing about all 3 methods is whatever I write in my box, you're going to see that term either in the vertical method or in the foiling method. So you can check your answer no matter which method I use. So you should have a 2n cubed somewhere. You should have a 12n squared, an 18n, and then coming down a negative 3n squared, negative 18n, and negative 18. Oh, negative 20. Thank you. I multiplied wrong. All right, combining my like terms. They're not always going to be on the diagonal. It depends on the type of problem you're given. But in this case, they are on the diagonal. We have 2n cubed Negative 3n squared and 12n squared add together to make 9n squared. Then negative 18n and the positive 18n make 0. And negative 27. So that would be your standard form of that equation. And our y-intercept, if we substitute 0 in for n, 0 in for n, we're left with negative 27. That's our y-intercept. Okay? It's just because our problem was an equation, so it was y equals. So I just carried the y all the way down throughout my problem. Okay? I've handed out your homework. I'm going to ask you to start on the back side, 9 through 15. I wrote all the answers on the whiteboard. I'd like you to check your answer as you work. Okay? And then I'm going to probably do number 15 with you in, I don't know, 12 minutes or so. We'll do it at the end of the period. Okay? Okay, so turning to problem number 15, they've given us the volume of a sphere is 4/3 pi r cubed, and they've asked us to use the radius of 2 minus x. So first we're going to substitute that into the formula for volume of a sphere. And that means we're going to have to cube 2 minus x. So first, I'm going to expand that. So we have 2 minus x times itself 3 times. And I'm going to do the first multiplication of 2 minus x times 2 minus x. When we do that, you get 4 minus 4x plus x squared. So now we have 4/3 pi times this trinomial times this binomial that we haven't used yet. So next, we need to multiply the trinomial by the binomial. So I'm not going to write it all out. You can use the box. You can vertically multiply, or you can FOIL. But it's going to leave you with 8 minus 4x minus 8x plus 4x squared plus 2x squared minus x to the third. I'm going to combine my like terms. Alright, last thing we're going to do is distribute this number out in front. So 4/3 pi, distribute it to each of the 4 terms. 4/3 as a fraction is going to be easiest if we have each of our coefficients as fractions. So for this first one, we have 4/3 times an 8 over 1. So I'm going to do the 8 times the 4 is 32 over the 3 pi. Next, we have 4/3 times 12 over 1. 12 times 4 is 48 over 3 times 1. We have the pi, and this term also has an x. We have 4/3 times 6, so that's 24 over 3. I'm going to reduce that in a little while. We have pi and x squared. And then lastly, we just have a coefficient of 1 times the 4/3 pi. Alright, so simplifying, 32 and 3 don't have any common factors. 48 and 3 simplify to be a 16. 24 and 3 is 8. So this would be our simplified solution. And if we wanted to find the y-intercept, which it's not asking for here, and in a typical problem like this, you probably wouldn't ever be asked for the y-intercept. But if we were looking for it, substituting 0 in for x, we'd be left with 32 over 3 times pi, which we could get as a decimal. Okay, happy homeworking.